C-star algebra will be assumed to have a multiplicative identity, which is necessarily self-adjoint, because one star is also multiplicative identity, so that these two must be equal and has known 1 thanks to these equalities, and we ignore the trivial possibility 1 equal to 0 implies that a equal to 0. We don't consider this trivial case, and we know important examples for C-star algebras. B of H is a C-star algebra, and in particular the set of all n times n matrix, complex matrix, and complex numbers are C-star algebras. And you can remember that for any subset S of a C-star algebra, there is the smallest C-star subalgebra of A denoted by C-star S, which contain S. Reason? C-star S may be defined somewhat as ordinal spaces generated by a set. Okay, the intersection of all C-star subalgebra that contain S. The intersection of all C-star algebra contain S. And you know this method. For example, the smallest sigma algebra generated by S, or other concept. So C-star of S defined in this C-star of S can be defined. C-star of S can be defined. Let me write C-star of S, the intersection of all A, for example, such that A is a C-star algebra, and also S be a subset of A. This shows that S is the smallest C-star algebra containing S. Okay, containing S. And describe more constructivity as the known closure of the linear span of all words in the alphabets 1, S, and S star. All words can be that we can make by this set. Okay, this is equal to 1 and all X and X star. The letter description in the previous sentences shows that C star of X is a commutative singly generated C star algebra if and only if we have this equality. It is very trivial, because C star of, if we consider S equal to this singleton C star of this S X is commutative if and only if we have this equality. This is very trivial because any element of this have this form. For example, x by this power and x star by another power. Okay, if we consider the multiplication of this also maybe we have more than 2 in this word. Okay, for example, we can say let me write this by this method n1 n2 and nn n1 n2 and for example x n3 up to the n x star nk. Okay, it is very trivial that if we have this equality we can change this and with this to a word by this form x by n power multiplied by x star by n power. Okay, and so if we have this equality, any word in this space can be commutative, and so this is commutative C star algebra. Such an element of C star algebra which commutes with its adjoint is said normal. This x is called normal. Okay, if sigma be any compact space, then C of sigma, the set of all continuous functions from sigma to complex number, is commutative C star algebra with respect to pointwise algebraic operation, and F star equal to the adjoint of F, and this supremum, it is well known example of C star algebra. And the definition of representation: a representation of a C star algebra A on a Hilbert space H is just a star preserving unital algebra homomorphism of A into B of H, so that a representation on a C star algebra is a star preserving unital algebra homomorphism, such as P, for example. Okay, P from A to okay, let A be a C star algebra a representation on A is a, please note that this is must be homomorphism, but algebra homomorphism and unital algebra homomorphism, unital algebra homomorphism, unital algebra homomorphism such as P, for example, from A to B of H, okay? Such that P is a star preserving and this must be a star preserving, and H is a Hilbert space, we know, such that and H is a Hilbert space. We know this. In this book, H considered as Hilbert space. Okay. So we must have these properties for this P. P from A to B of H have these properties that for any for example X and Y in A, P of XY equal to P of X, you can write O because the multiplication in this algebra is composition, and also P of X plus Y must be equal to P of X plus P of Y, and also if consider any complex numbers, P of alpha X equal to alpha P of X, and this must be preserved norm so that preserved star P of X star must be equal to the S star of P of X. Okay, and we know that this is equal to the add, then we say that this is an representation Pi from A to B Hi, I equal to 1 and 2 are said to be equivalent if there exists a unitary operator U from H1 to H2 such that we have these equalities. For any A in A, P2 of A equal to U, P1 of A, U star. Okay. And we have this remark. Please read this. It is very important. A, B, and C, and you know this. This review these four representation, and also we have this proposition: let sigma as a subset of R be a compact set, and let F0 be in C of sigma, be given by f0 of t equal to t for all t, so that this is identity map. If x belongs to b of h, is a self-adjoint operator such that a spectrum of x be a subset of sigma, then there exists a unique representation P from C of sigma to B of H such that P of F0 equal to X. And conversely, given any representation P from C of sigma to B of H, it is the case that P of F0 is a set adjoint operator X satisfying sigma of X is a subset of sigma. And this is the proof of this is not difficult. To begin with, if x belongs to b of h, is a self-adjoint operator such that sigma of x be a subset of sigma, then it follows from the inequality 1, 5, 12. Please follow this. That the norm of p of x in b of h is less than or equal the norm of p in C of sigma of h, and this is less than the norm of p in C of sigma for any polynomial p. We see this, okay? It is easy deduced now from Weierstrass theorem that this mapping any polynomial map to p of x, polynomial in the set of all polynomials by complex coefficients, and P of x in B of h extend uniquely to the star homomorphism that you need from C of sigma to B of h. Conversely, it is easily seen that f0 minus lambda is not invertible in C of sigma if and only if lambda belongs to sigma, because this must be non-zero in all elements. And as p preserved invertibly, we find that sigma of x equal to sigma of p of f0, and this is a subset of sigma of f0 equal to sigma. Okay, so we have this nice proposition. Remark: representation pi from C of sigma to B of hi are equivalent if and only if the operators pi of f0 are unitarily equivalent, because generated by image of the generators. Okay, because representations are additive and multiplicative. Okay, and the definition of cyclic representation and measures. Assume for the rest of this book that sigma is a separable compact metric space. Suppose P from C of sigma to B of H is a representation. So we consider this C star algebra, okay, of C of sigma on a separable Hilbert space H. Definition: a representation P from this to this is said to be cyclic if there exists a vector x in H such that P of C of sigma of x is a dense subset of X. This is a subset of H, okay? Let P definition. Let P from C of sigma, for example, to B of H be a representation. And X belong to A. X belong to H, okay? X must be an element of H. X is called a cyclic vector. X is called a cyclic vector whenever P of C of sigma of X be dense in H, or equivalently we know that P of C of sigma of X equal to this set, the set of all PF of X, such that F belong to C of sigma, okay? This set equal to, we must take the closure of this. If this equal to H, then we say that this set or this vector is a cyclic vector. P of C of sigma, so that we must consider all PF for all F in C of sigma. And please note that P is a function from this to P of H, okay? So for any F in C of sigma, P of F is an element in B of H, okay? P of F must be belong to B of H, so that for any F in C of sigma, P of F of X is an element of, let me write one more step, P of F is a function from H to H, is the bounded linear function from H to H. So for any F in C of sigma, PF of X must be belong to H, okay? So that these elements are in H. Now if the set of all these elements as a subset of H be dense in H, we say that this X is a cyclic vector. Is a cyclic vector. Okay. In such a case, the vector X is called a cyclic vector for their representation. If such a vector exists, one can always find a unit vector which is cyclic for the representation. If we have one cyclic vector, we can find an unit vector. Okay, this is very trivial. And we have this lemma. If Si equal to this set is a set which linearly spans a dense subspace of a Hilbert space Hi. Okay, so the closure of this equal to Hi, and if we have this equality between inner products for all j and k in lambda, then a unique unitary operator such as u from h1 to h2 such that we have these, and the proof of this is easy. You can follow in the book. The proof was very easy and simple, but we have this proposition: if dear student, do you have my voice? Thank you very much. If mu is a finite positive measure defined on the Borel subset of sigma, then the equation P mu of f of g equal to fg for any f in C of sigma and g in L2. Define a cyclic representation such as P mu of C star with cyclic vector g0 equal to 1. So please note that we have a positive measure and we define a representation. This representation is from C of sigma to B of one Hilbert space. We consider Hilbert space L2, okay? So this map from this to B of L2 of, this is 2, okay? L2 of sigma and mu, sorry, L2 of sigma and mu, because we know that L2 is a Hilbert space, so that this is all Hilbert space in this case. Now we define for any f in C of sigma P mu of f, a function from L2 to L2 defined by this. For any g in L2, P mu of f of g equal to fg. And we know that this fg is an element of L2 again, fg. Okay, and conversely it is very nice because we can prove easily that this is a cyclic representation, and one is a cyclic vector for this representation, but in the context any representation of sigma to B of H, representation with cyclic PB, or if P from C of sigma to B of H is a representation, arbitrary, okay, with a cyclic vector X, then there exists a finite positive measure mu defined on the Borel subset of sigma and a unitary operator U from H to L2 of sigma and mu, such that mu of X equal to G0, and we have this equality for any F in C of sigma. And 3, in the setting of 1, there exists a unique representation such as pu mu tilde from L infinity of sigma and mu to B of L2 of sigma and mu, such that we have 1, the restriction of this p mu tilde to C of sigma equal to p mu, and 2, if we consider this set, the set of all Fn n equal to n, such that this supremum be finite and Fn tend to, or Fn converges to F mu almost everywhere, then this subtraction, the norm of this subtraction in L2 converges to 0 for any G in L2. The proof of this is not difficult, okay? And you can follow this. For example, it is fairly clear that this function is a representation, and we have this inequality. We can check all of this because, for example, by this function rows, okay, let me write p mu of f let mu be a finite positive measure on sigma algebra What is our sigma algebra? Borel sets. Let me write on the Borel subsets of this set. This is a set, okay? This is not a good symbol. This is a set, not summation, denoted by this. We can denote this by E, and it be more better. But in this book, this set denoted by this sigma. Now we define P mu from C of sigma to B of L2 of sigma and mu as all Hilbert space. Okay, by this function rules, for any f in C of sigma, we know that p mu of f must be an element of this, so that must be a function from L2 to L2, so that we must define the action of this function on any element in L2, G to L2. Let me write smaller. F in C of sigma and for any G in L2 of this set and this measure, okay, mu. P mu of f of G defined by Fg. And it is very clear that this is representation. For example, this is linear. For example, if f1 and f2 belong to C of sigma, then we see that P mu of f1 plus f2 equal to P mu of f1 plus P mu of f2, because for any element in L2, P mu of f1 plus f2 of G equal to f1 plus f2 multiplied by G, and this is equal to f1G plus f2G, and this is equal to P mu of f1 G plus P mu of f2G. We can write P mu of f1 P mu of f2 of G. This holds for all G, so that we have this equality, okay? And also this must be an algebra, okay? It is very trivial that P of alpha for any alpha in complex number, for example, P mu of alpha of G equal to alpha f of G, and this is equal to alpha fg, and this is equal to alpha P mu of f of G, so that this holds for all G, okay? So that P mu of alpha f equal to alpha P mu of f, and also P mu of F1 F2 of G equal to F1 F2 of G, and this is equal to not of, this is multiplication, okay, by all definition, and we can write this is equal to F1 of P mu of F2 of G. This is equal to P mu of F2 of G, and then this is equal to P mu of F1 or P mu of F2 of G. So that this holds for all G again, for all G in L2 of sigma and mu, so that P mu of F1 F2 equal to P mu of F1 P mu of F2, and also this function is a star preserving on the other hand P mu of bar, because we know that the star operation in C of sigma is bar, equal to P mu of F bar or you can say a star in B of H, okay? So we see that in the proof of this in the book that it is very clear that this is a representation, and also we have this equality, we have this equality. It is very trivial because please note that in this Hilbert space L2 if we consider, for example, F and G in L2 of this space, this is the inner product of this space, okay? F and G equal to the integral of F G bar, okay? So if we consider any F for any F in C of sigma if we consider and for any G in L2 if we consider C of P mu of this F you know that P mu of it is an element of B of H or B of L2. Of G or we can write G1 and G2 if we consider this is equal to by the definition of adjunct G1 and P mu of F G2. Okay. And on the other hand, this is equal to G1 and the definition of P mu is FG2. Now if we consider P mu of F bar, okay, this is F bar and this is F bar. And this is equal to by this inner product G1 F bar G2 D mu on sigma. Okay. And if we consider on the other hand this and G2 this is equal to equal to which function What is f? Please you see this. Okay, p mu of f equal to this. And this assumption okay. So this is equal to G1 P mu of F of G2, and this is equal to G1 FG2, and this is equal to this integral. G1 FG2 by d mu. Okay, we must take a bar. I don't like this bar. So we have this bar in whole of this, and this is equal to G1 F G2 bar. Okay. And so in this also we have this integral on sigma G1 okay, dear students, please. Oh. Okay, so we see that this proof is for A star preserving, okay? P mu of F bar, if we consider P mu of F bar, this inner product equal to, oh, we have a mistake in this. we have a mistake in this line because so we must delete this. I'm very sorry. Okay, this is equal to f bar multiplied by g. By the definition of f bar, definition of p of mu, and this is g2. Now this equal to آقای جعفری برید C34 مختاریه مال اون شرکت داره زنگ میزنه. اگه زنگ زد بگو که مدیر مالی رفته مکه، واقعا هم بگو سر کلاسه جواب نمیداره. Okay, and this is equal to the integral of f bar g1 g2 bar d mu on sigma. And exactly we have this for another. I'm very sorry for this mistake. This is very simpler. We don't have this line. Okay. We have these two equalities. P mu of f bar of g1 and g2 equal to this, and P mu f star of g1 and g2 equal to this. By this inner product, so it is better that we say for any g1 and g2, okay, for any g1 and g2, g1 and g2 in 2 we have this. This shows that these two shows that P mu f bar equal to P mu f star, P mu f star, and this shows that P mu is star preserving. Okay, star preserving. This and this implies that the mu is star preserving. So it is clear actually that this is a representation, and also we have this equality because the norm of P mu for any f in C of sigma, the norm of P mu F in this space B of L2, okay, equal to this supremum norm of P mu of F of G such that G belong to L2 and the norm of G be less than or equal 1. This is the definition of operator norms, and also we know that this is the norm of L2, okay. And by our definition, this is equal to the supremum of the norm of Fg. This is very simple, such that G belong to L2, sigma and mu, and the norm of G known to be less than or equal 1. But it is, let me write a note such as a star, okay. It is very easy that if we consider Fg, this norm equal to the integral of Fg to the power of 2d mu on sigma and then by this power, okay, L2. And we know that this is less than or equal this integral, the norm infinity of this, and then G to the power of 2 d mu, this holds because we know that it is to the power of 2, because we know that the absolute value of F is less than or equal the supremum norm, okay, or essentially supremum norm. So this is less than this. This to the power of 2 is less than this to the power of 2. And so we can move these numbers to the outside of integral, so that this is equal to the norm infinity of this to the power of 2, this integral G to the power of 2 d mu, and all of this by this power. This power and this power can be omitted, and we have this norm, infinity norm of F, multiplied by this integral G to the power of 2 d mu sigma by this power, and we know that this is L2 norm. This is equal to this multiplied by this, and also we know that this is less than or equal 1, so that this is less than or equal the infinity norm, so that all of these are less than or equal this, so that the supremum must be less than or equal the infinity norm of less than or equal the infinity norm of F. This holds by a star, okay? This holds by a star, because all of this is less than or equal this. So we see that the norm of P mu of F in B of L2 is less than or equal to the infinity norm of F. And clearly P mu of F is normal, and all of this item is very trivial. Let me write a sentences for you. We want this lesson be, this session be the last session of this course, okay? This session is the last session. And translate to Arabic. Okay.
معتبرا أن هذا الاجتماع هو آخر لقاء لهذه الفئة، أترك لك قراءة بعض البراهين.
Okay, do you understand? Please read this proof completely. I begin this proof and prove that this is a representation and we have this inequality. Other steps are in your books and very easy. Please read this proof from this book. You use this representation theorem in the proof of 2, and it is very nice proof. And let's write the proof of this theorem as an homework for me, okay?
من فضلك أرسل لي الدليل الكامل لهذه النظرية مع التفسيرات الكاملة.
Such as this that we write for you, okay? For example, this norm is less than this because we have this relation. It is right completely with details, and we have an important topology called a strong operator topology in B of H. A sequence xn, for example, in B of H is said to converge in the strong operator topology by this operation. SOT. If for any x in Hilbert space H, xn of x converges in norm of H or Hilbert space, okay? So this sequence in B of H is said to be converged in the strong operator topology if and only if for any x this sequence in H, because xn is a function from H to H, so that xn of H belong to H, and this is the sequence in H. If this sequence must be converged in H, it is the consequence of the uniform boundedness principle that in this case the equation x of x equal, because we know that this limit exists in H. Now we can define this function for any x of x equal to this limit. This limit exists. Define a bounded operator in B of H. We shall abbreviate all this by writing xn tend to x in SOT topology. Okay? So that if xn belong to xn belong to B of H, then xn and from 1 up to the infinity, okay? Is converged in SOT topology if and only if for any x in H this sequence xn of x, okay, n from 1 to infinity in H is converged, okay? This is very important. For any x, this sequence must be a convergence sequence. Convergence sequence. Okay? Converge is converged. And this holds if and only if there exists x in B of H such that for any x in H, x of x equal to this limit, because we know that this limit exists, okay, and tend to the infinity. So xn tend to x in SOT, strong operator topology, equal to for any x in H xn of x to x of x in H, okay? This is a very important and useful topology on B of H, because you know that we have another topologies in B of H such as the norm topology, okay? But this is another topology different from norm. We record a couple of simple but very useful facts considering SOT convergence. But first recall that a set S as a subset of H is said to be total if the linear space expanded by S is dense in H. And we have this lemma: the following condition on a sequence Xn in B of H are equivalent. Xn converges to X in SOT for some X. This supremum must be finite and there exists some total set S such that Xn of X converges for all X, and this supremum is finite and there exists a dense subset M of H such that Xn of X converges for all X. This is the part 1 of this lemma. And 2, if sequence Xn, two sequence Xn converges to X in SOT and Yn converges to Y in SOT, then this multiplication converges to XY in SOT. The proof of this are very easy. Please read the proof of this and write for me, okay? Again, and another homework, this is very easy. And also we have this theorem: if P from C of sigma to B of H is a representation on a separable Hebel space H, there exists a countable collection mu n for some countable set n of probability measures defined on the Borel sigma algebra B sigma such that P is unitarily equivalent to this representation. Okay, only read this theorem without proof, okay? We don't have any time, and so I omit the proof of some theorem. Without proof, okay? Read without proof. So we deleted the proof of this theorem. And after this, we have this lemma and this theorem with proof. Okay? It is enough, but we added to definition. One of these is von Neumann algebras. Let me find this. Let me find this for you. Okay, in this. Okay, from first of this appendix, this appendix. We briefly recall here the two non-trivial theorems for major theory that we use in this book. They are Rees representation theorem and Lucian. You know both of this theorem, dear students. And in this section, recall these two theorems, and it is maybe good for you. But we have this lemma, C of sigma is dense in LP. It is very, very important. Continuous function are dense in LP. And we omitted the proof of this. Only please know that the set of all continuous function is dense in LP for any P. Okay? And also this lemma that it proved by the Lucian theorem, and this definition, one of many equivalent definition of one Newman algebra. This one Newman algebra is very, very important algebra, is as a unital star subalgebra of B of H, which is closed in the SOT. So any unital star subalgebra of B of H. Okay? Definition. Any star subalgebra and unital star subalgebra in B of H that is closed under SOT is called a one Newman algebra. One Newman, but this spell Newman algebra. Okay, please understand this definition for one Newman algebra, and this is the definition of a strong operator topology that we call again for you and also prepare a basis for this topology. And other definition is this. It is very easy. Let A denote a unital norm algebra, not necessarily Hilbert space. A denote a unital norm algebra over all field F. This F can be real or complex numbers. Thus A is norm algebra with a unit element 1 such that we have this. Okay? And let A prime denote the dual of A. A space of all continuous linear functional on A. You know all of this. Let SA equal to the set of all x such that the norm of x equal to 1, and for any x in SA, define D of A and x equal to the set of all f in A prime such that f of x equal to 1 and this equal to the norm of A. So that we have this definition. Let A be a unital norm algebra. Okay, norm algebra. And okay, S of A, we know S of A equal to the set of all elements in A such that norm of A equal to 1. Then we define D of A and X, Di for any X in SA, D of A and X equal to the set of all linear functional such that we have this equality. The set of all elements in the dual of A, linear bounded functional. The set of all f in the dual of A such that f of x equal to 1 equal to the norm of f. Okay, and then we define for any A in A and X in SA. For any A in A and for any X in SA, we find this V of AX, V of A, this element and this element equal to the set of all FAX such that F belongs to D of A and X. And finally we have these two V of A and A equal to the union of this set. V of A and A equal to the union all V A sets. Okay, this equation, and V of A equal to the supremum of these. VA equal to the supremum of absolute value lambda for any lambda in V of A and A. Then this V of A is called the numerical range of A, and this is called numerical radius. V of A and K is called numerical range. Okay, definition. V of A and A is called the numerical range of A, the element A. And V of A is called the numerical radius for A again. Okay, these two definition is important. Radius for A, and this two definition have many simple properties, such as these inclusions and equalities and this lemma and this theorem. Okay, for each A in A, V of A and A is compact convex subset of F. Proof is very easy, but I omitted the proof of these items. Okay, dear students, we have a long session because this session is the last session of the operator theory courses. Thank you very much, and see you in Iran inshallah. Thank you. Goodbye for now. Goodbye.